So today we are going to discuss about the what I'm naming the targeting the maximum heat recovery in a process. So what we have seen up to now is that the recovery from heat in a process can be done by installing heat exchangers that would recover the heat of a hot stream in order to heat up a cold stream. That's what we have done. And last week we have seen that this needs an investment. So we have to buy one heat exchanger. And what we have shown as well is that the cost of the heat exchanger depends on what we have named the delta T minimum. It's the minimum temperature difference between the hot and the cold streams. That might happen on one hand or on the other hand, depending on the MCP flows. And as soon as we change this amount of this value here, we know that the heat that we can recover, which is shown here between this line and this vertical line here, if I'm decreasing the value, the heat is going to increase, the heat recovery is going to increase, and by increasing the heat recovery, I will reduce the amount of heat that I need to buy to satisfy the needs of the cold stream, and I will at the same time reduce the amount of heat that will be released in the environment in order to cool down the hot stream to its target temperature. Okay, we have been then calculating what it means to find the best value, and we realized that it was a compromise between the expenses in the operation, which is the operating cost expenditure here, and the amount of money that we will spend in order to buy the heat exchanger, which is here the investment cost. And the investment cost, we have seen that there was a formula that allows us to calculate based on the area of the heat exchanger that is here to estimate the cost of the heat exchanger. Then we have to analyze the cost as a function of the interest rate and the number of years during which we will use the heat exchanger. That allows us to compare the investment cost in Swiss francs per year with the operating cost in Swiss francs per year. In order to calculate this, we can see that the amount that we will spend is a function of the cost of the cooling utility and the cost of the hot utility, and the cost is multiplied by the amount, which is what is needed for the cooling minus what is recovered, and here the same, what is needed for heating minus what we recover. And we multiply everything by the operating time. And when we have this, then we can compare the expenditure in terms of energy and the investment that is needed as a function of the temperature difference between the hot and the cold streams. So the smaller the temperature difference is, so if we go in this direction, the bigger will be the heat exchanger, so the highest will be the cost. And at the same time, the energy savings, as soon as we decrease the delta T minimum, the energy savings are increasing, which means that the cost of the energy is decreasing. And when we make the sum, when we compare the Swiss franc per year spent in energy and spent in reimbursing the heat exchanger that we have to buy for the heat recovery, there is an optimum point which is located here, which defines the best value for the delta T minimum, which is a point at which if I'm investing more, it means that I'm going in this direction. The savings, so the reduction here, will not be compensated by the increase of the cost. And the same in the reverse direction. If I'm spending a little bit less in heat exchange area, okay, then the increase of the energy bill will not compensate the savings of the investment reduction. Okay, so it's a best point, and it means that as soon as you know this, you are not allowed to work with another value. Okay, because it's the value where in both directions you are always winning money. Or if you depart from this value, each time you move from this point, you are losing money. Okay, so normally your boss will not be happy. Okay, So we have seen that this is depending, of course, on the different conditions under which we are working. So how much hours we will operate, what is the heat transfer coefficient, so the quality of the heat exchangers, the size of the heat exchanger, the cost of energy, which is everywhere, so here and here, the type of heat exchanger, of course, and the investment strategy. So it means that if the financial officer of your company is asking you a big return or not, you will have different decisions that will be taken concerning the delta T minimum that you will consider. So now the question is that in reality, if I'm going into a process, there is more than one heat requirements. That means that I will have more than one hot stream and more than one cold stream. So for example, here I have a stream that needs to be heated from 20 to 130. I have another one that needs to be heated from 80 to 140. And then here I have a stream that needs to be cooled down from 160 to 60 degrees C, and another one that needs to be cooled down from 150 to 50 degrees C. Okay, so it means that now I have more than one hot stream and more than one cold stream, right? So first, before asking you the question, so what is important is that the temperatures that are here, so the 20 and the 130, or the 80 and the 140, are temperatures that are imposed by the process. So it means that the process needs a certain temperature here at the entrance of this unit here. It is going to deliver after this, which is probably a reactor here, it will deliver a certain temperature here. Okay? And it needs to reach this temperature, the 60, to realize this next operation. Okay? So it means that all those temperatures are imposed by the process units. Okay? So now, my question to you is, let's take this example, and let's assume that you have taken, you will take a delta T minimum of 10 degrees C. So by the way, using 10 degrees C, what does it mean? It means that it's easy for the teacher to use 10, because 10 is easy to divide by 2, which makes 5. Okay, so it's easy to deduce 10 or to add 10, okay? But in reality, you should use the value that you have calculated, okay, depending on the place where you are. But let's assume that in this case, the 10 degrees C makes sense, okay? Assuming a 10 degrees C temperature difference between the hot and the cold streams. So what I would like to know is what is the amount of heat that you can recover out of this system? So I have 2 hot streams, 2 cold streams, so a priori I can recover heat. So what is the amount that I can recover? And I would like therefore to know what is the amount here that I should spend in the boiler here. So I'm going to recover, so it means that I'm going to reduce the amount of fuel in the boiler. I would like to know how much. And here I have a cooling water that is used, and I would like to know how much I will reduce the amount of heat removed by the cooling system. Okay? So I would like you then try to solve this problem. So you have 2 hot streams, 2 cold streams, and I would like to know what is the expected bill that you will have to pay here if you install heat recovery, heat exchangers. Okay? So create small groups and try to calculate what is the maximum amount of heat that can be recovered by heat exchangers. So, if we look back to perhaps I will ask you first before what is the solution? So, what did you find? What is the amount of fuel that you will spend in the boiler here? Do you have a value?
Minimum value?
Yeah.
65 kilowatts.
So 65 kilowatts instead of
200.
So what is the total heat load of the boiler now?
So instead of 405 kilowatts.
Say it again.
Instead of 405 kilowatts.
405 kilowatts. Okay, and the solution of your group is
65 kilowatts.
65 kilowatt. Okay. The other groups?
50.
Huh?
50.
You have 50. So 1, solution 2 is 50. No?
65.
65.
65.
Also 65.
65.
65 also. Okay? Right. So, something which is interesting here is that you have two different solutions, which means that there are options. Okay? So, what were the difficulties that you have observed?
Like the decision making process part. For example, if we are going to use the top part for the top part, or if we are going to use the top part for the bottom part of the hot and cold streams.
Yeah, so the first difficulty is which one with which one? So which hot stream is connected with which cold one? And as soon as you connect, what is the second difficulty? What was the difficulty when you decide which one is connected with which one? It's a delta T, so you do not know where the delta T minimum is located. Is it before or after, at the hot end or the cold end of the heat exchanger? Right? So you have a combinatorial problem, okay, and you have a difficulty of identifying the delta T minimum. So I will not ask you to describe the two solutions because it seems that there was a group that would have won the market, 50 degrees C, 50 kilowatt, while the other one would have a less good solution. Okay, and you are not sure about who is wrong, because most probably you will challenge the other one, saying, okay, but they have not reached the delta T minimum in the heat exchangers, perhaps. Okay, so let's try to see if there is a systematic way of solving the problem. And the systematic way will be done by first realizing that when we install a heat exchanger, we have always one hot stream and one cold stream. So it means that the heat exchanger is always exchanging heat between a hot stream that needs to be cooled down and a cold stream that needs to be heated up. So the same happens in my system, and I'm going to define the hot and the cold streams. So a cold stream that needs to be heated, that is going to go from 20 to 130. Another one that needs to be heated from 80 to 140. So those are the cold stream. So pay attention to the fact that they are cold streams, but they are not cold in terms of temperature. Okay, they are just cold because they need heat, right? And the same is for the hot stream. So there is one hot stream that needs to be cooled down from 160 to 60, and another one that needs to be cooled down from 150 to 50 degrees C. Something which is important again here, the two temperatures are what we name the origin temperature imposed by what is happening before, and the target temperature that is imposed by what is going to happen after. Okay, so the two temperatures are imposed, and we are characterizing the heat flow by the MCP times the MCP, so it's the mass flow, kilogram per second, multiplied by the kilojoule per kilogram per degree C, which makes the product makes kilowatt per degree C. Okay, it's the amount of heat that is needed to decrease the temperature by 1 degree C in this heat exchange here. So when I'm analyzing a process, I will have exactly the same. So I will have a collection of streams to be heated and streams to be cooled down. Okay? So to be heated here, to be heated here, to be cooled down here. Okay? And I will have a collection. Okay? And what we can say is that all those streams, being hot streams or cold streams, start with a known inlet state that is coming from the process units or from the environment, and needs to reach a target state that is imposed by the process unit operation or by the environment. And what we are doing for the moment, but it is not necessarily the case always, but for the moment we are going to consider that the Cp is a constant. So it means that this formula, which is officially defining the heat load as being a function of the mass flow here, and the integral between the inlet state and the outlet state of the variation of the heat as a function of the temperature, can be assimilated to this linear equation here, where I have the MCP, I have the mass flow times the specific heat multiplied by the temperature difference between the inlet state and the outlet state. And I give you here some examples of hot and cold streams that we can see in the reality. So, for example, a hot stream can be the heat that is delivered at the level of the distillation condenser. It's also the heat that is delivered by an exothermic reactor. It's the heat that is delivered by the combustion gases that needs to be cooled down. Okay? It's also the heat that is delivered by the steam that is condensing. Or it's also the hot stream of a refrigeration cycle. So when at the higher pressure of the refrigeration cycle, I will deliver heat, even if it is just to deliver heat to the environment in a cooling water. So those are examples of streams that are named the hot streams that needs to be cooled down. And the same for the cold stream. So the boiler of a distillation column, the reactant that needs to be preheated in a reactor, the cooling water is a cold stream that will be heated. The steam that needs to be produced is a cold stream, or the cold stream of a refrigeration cycle. Okay, so again, hot and cold does not mean that the temperature is high or low. It just means that a hot stream delivers heat and a cold stream is received or is asking for heat. Okay? So it means that now if I'm going back into this system, I'm going to characterize the streams, and therefore I'm going to write down for each of the stream, I give them a name, A, B, C, and D. I am characterizing the temperatures at the inlet, the temperature at the outlet, the MCP that allows me to know what are the heat load that are needed or that are available in the different streams, and therefore I will have the cold streams that needs to be heated. And if you look at this, you reach the 405 that has been calculated here, which is the amount of heat that is delivered by the hot utility that is giving you the heat to heat up all the cold streams here. Okay? So the sum is 405, which can be seen here. That is what is needed by the cold streams. And then we have the hot streams that needs to be cooled down from an inlet state to an outlet state, and for which we have also a total heat load available. So what you can see here is that you have 450 kilowatt of heat available in the hot streams. Okay, so apparently we have too much heat in the system because we have more heat in the hot streams than the heat that is needed for the cold streams. Okay? So now the question is why none of you have identified that there was a solution where we just need a cold utility, because officially there is enough heat here. Okay? So now the question is, because this is just the inventory of the streams to be heated and streams to be cooled down, and then you were saying, okay, but we have to limit our temperature to difference to a certain value that you impose. So it means that when we connect streams, there are some limits that needs to be reached. Okay, that most probably explains why you are reaching 65 or 50. And I guess that those two values is mainly because one has started with this one and another one has started with this one. Okay, it's just a question of identifying the priorities. So now let's consider that we have those two streams. Forget about the temperatures, but at the end what I know is that I have a stream that goes from this temperature to this one, which is the stream A, and I have another one that goes from this temperature to this one, which is the stream B. Okay? And what I'm going to do now is to make the inventory as a function of the temperature of the heat that is available. So what does it mean? It means that I'm going to look at from this temperature to this one, only the stream A is present. So it means that from there to there, I have a given amount of heat available. Then from this temperature to this one, it appears that I have the stream A that can deliver heat and the stream B that can deliver heat. So it means that I can do now another slope which calculates the amount of heat that is available between this temperature here and this one. And then afterwards, from this temperature to this one, I have only one stream, the stream B, which then is going to deliver a certain amount of heat. Okay? The heat load being Cp times the temperature difference. Okay? But if I'm doing this, then I have a profile of the heat that is available as a function of the temperature. Okay? And it is measured in the heat temperature diagram. So it means that as a function of the temperature, I know what is the amount of heat that is available in all the streams that needs to be cooled down. Okay? This composite curve is named the hot composite curve. So this curve is named the hot composite curve. So it defines the process as being a hot stream to be cooled down. Okay? So compared to what we were doing last week, the only difference is that now the curve here is not a straight line. Okay? It is a collection of segments. Okay? Now I can do the same with the cold streams that needs to be heated up. So I can take the two cold streams that needs to be heated up. I can then create as well a composite curve in which I will calculate from the lowest temperature to this one. I have only one stream, then nobody here, and then from there to there I have again a single stream, which allows me to have a curve like this. So from this temperature to this one, then nothing between those two temperatures, and then afterwards again heating up. Okay. Now I have at the same time the temperature enthalpy profile or the heat temperature profile of the heat that is available in all the streams, hot streams in the process, and at the same time the temperature enthalpy profile of all the heat that is needed by the processes, okay, by the streams in the system. Well, now I can consider that this blue curve here, which is named the cold composite, okay, is like a cold stream to be heated up. Okay? And now I can say, okay, but if I have a hot stream that needs to be cooled down and at the same time a stream that needs to be heated up, then I can perhaps do a heat exchange that will be limited to the temperature difference. So what I'm going to do is that I'm going to move this curve in an horizontal way until it reaches the delta T minimum, so the temperature difference, which is the minimum that I have imposed. Okay? And by doing this, then I will realize that, okay, I can make this disappear first. I can realize that I can calculate how much heat can be recovered between a very big heat exchanger that would consider all the streams that enter into heat exchange and that will deliver heat, and all the streams that need heat. Okay? So it means that now I can calculate the amount of heat recovery between the hot streams and the cold streams. And by this plot, I know that the temperature difference between the hot and the cold streams is always higher than the minimum temperature that I have imposed and that I have calculated last week. Okay? So it means that I have identified what is the amount of heat that needs to be, that can be recovered. Okay? And now by balance, I can calculate as well the amount of heat that is still missing for heating up all the cold streams up to the temperature that they have to reach. Okay? So it means that now I know how much heat I have to buy after I have made the heat recovery. And the same is true for the amount of heat that needs to be evacuated out of the system. Okay? So the hot streams needs to be cooled down up to a given temperature. I have made a certain recovery here, which means that the rest needs to be taken out of the system by cooling water. Okay, so now I have defined what is the maximum heat recovery in the system. Okay, to summarize, as soon as I'm plotting the temperature enthalpy profile of making the integral of all the heat that is needed by all the streams that needs to be heated in a system, and I'm making the same for the hot streams that needs to be cooled down in a system, I can read, as soon as I have defined the minimum temperature difference, I can read the amount of heat that can be recovered in a system. I can read the amount of heat that still needs to be supplied to the system and the amount of heat that needs to be taken out of the system by a cold utility. Okay? And the beauty of this is that it does not limit to 4 streams. Okay? I can do it with a complete process. Okay? I can also do it with several processes that are on a given production site. Okay? I can do it for a city, because each house has streams to be heated and streams to be cooled down. So you have to heat to produce water, and you will have wastewater leaving the system, so you have a hot stream and a cold stream there. Okay? And this kind of analysis can also be done. For example, there have been studies in the harbor of Rotterdam, where you have 100 of different industrial processes in a given site. Okay? They can all exchange deliver heat and release heat, which means that you can make those composite curves for very big sites. And it will be calculated exactly in the same manner. You make the inventory of all the streams that need to be heated. You generate for each of them the temperature enthalpy profile. You do the same for all the streams that needs to be cooled down. You build a composite curve, and then you match the hot stream and the cold stream, and you define the heat recovery that can be done. So this is really important, because you can then make the assessment, and it is quite fast. Okay? You can make the assessment of what can be recovered in very big systems, okay? Without having to make all the possible combinations like you have started to do when I did ask you today the way to solve the problem. So today you have a very new way of looking at this kind of problem, because now you know that first you make the inventory of all the streams to be heated and cooled down. You characterize them in terms of temperature enthalpy profile. You calculate the composite curves, okay? And you are able to calculate the heat recovery. Yeah?
I just have a question regarding the slope. So the slope is 1 over m.cp, right?
Yeah.
And on your previous slide, I think that cp is equal to a plus b. Does that refer to the ABCD that we introduced in the table?
Yeah.
So, but shouldn't we be?
So I'm not indicating here the slope. Huh? I'm just indicating that it is the stream A.
Okay.
Okay. So you're right. It's the slope is 1 over Cp.
Okay. And so just from where do we know exactly how we compose like the points? So it's like.
So the way you decompose is that each time you see a new temperature,
It's where we break.
You break. Because you know that, so said in another way, you do the integral, okay? You progress temperature by small steps, and at a certain time there is a new one that is coming in the list. And then after a certain time, there is one that is disappearing from the list, okay? And in the meantime, you know that the CP is constant, so you do not have to make step by step, because you know where is the next cut, okay?
Sorry?
Yeah.
Why did you move the cold outer and the hot?
The only thing that is important is that it has to be horizontal. But in fact, there is no reference. The reason why I'm starting here is that because I have attached here this one to 0 here. But you will see when you will use software, because we will give you a software to make those calculations, that nothing tells you where is the reference. Back to the thermodynamics, the reference is a convention. There is no absolute value. Okay? So it's the same here. I could have also moved the red to the blue. It would not have changed the results. Okay? Okay, so just perhaps some important indications there is that on the one hand we have identified what we name the pinch point. So the pinch point is the place where the two curves are the closer one from the other from the value of the delta T minimum that we have previously calculated. Okay? And this value is telling us that this is the temperature difference that will justify an investment with respect to the energy savings. Okay? So it means that the value that you obtain here, the heat recovery, although I do not know how many heat exchangers I'm going to buy and how much they will cost, at least I can make the assumption that they are in a situation where the investment will make sense with respect to the heat recovery that is realized. Okay? So it means that it's not a value that is calculated, that is a theoretical value. Okay? It's a real value that has an engineering meaning, because behind this there is a limit, which is an economical limit. Okay? Which means also that if I'm doing the same analysis in Belgium, France, or States, okay, I will not have the same answer. Okay? And of course, it depends on the value of the delta T minimum that you have calculated before. The other thing that is important here is that it's the important role of the energy balance. Because here, from this point to this one, is the total amount of heat that is needed by all the cold streams that needs to be heated. Okay? And what I can conclude is that the amount of heat that has to be bought to satisfy the total amount of heat that is needed, which is this one, that we name the hot utility. The hot utility is equal to the total amount minus the heat recovery. Okay? And the same for the hot stream. So the amount of cooling water that is needed in order to cool down all the hot streams is equal to the total amount of cooling needs of the holder's hot streams minus the amount of heat that is recovered by installing heat exchangers. Okay? So this is the second element which is shown here. So it means that the heat balance are obtained by making the sum of the hot and the sum of the cold. You fix a delta T minimum which has an economical value, and then what you obtain is the minimum heat requirement as a hot utility, so how much heat you have to buy to close the needs of the cold streams. You can calculate the amount of heat that can be recovered, which is the needs of the cold stream minus the hot utility, or the needs of the hot stream minus the cold utility, and that the cold utility requirement is equal to the heat that is entering the system with in form of the hot streams that needs to be cooled down, minus the heat that is needed by the cold utility, plus the heat that is entering in form of hot utility. And something which is important in this last formula here is that this is independent on the amount of heat recovery. Okay? Just because it's closing the energy balance of the whole system. Okay? And this is always true. So it means that the energy that is leaving the system is always equal to the energy that is entering the system minus the amount that is used in the process. No escape to this. Okay? No heat recovery. The amount of heat is equal to the amount of the cold streams. Okay? And the balance is going to be the hot minus the cold minus the hot utility plus the hot minus the cold, which will be released in the cold streams. And it's always valid. Okay, very important because it means that it will define what we name the more in, more out principle. Okay, so just some conclusions. It's written in small letters because you will just read it on the PDF. I will just give you the message. So there is no limit on the size of the system. Okay. Of course, if you have to connect, like in the harbor of Rotterdam, processes that are 40 kilometers one from the other, because it's a huge city of industrial processes, there will be the need to transport heat from one place to another, which means bigger delta T minimum in reality, okay? But the method can be applied independently of the size of the system, okay? The method can also be applied in smaller devices or big systems, okay? So for example, I can take a car and identify streams to be heated and streams to be cooled down. The hot gases coming out of the engine, the cold air that has to be preheated to heat up the inside of the car. Okay, so all those elements define hot and cold streams that can be handled by the same approach. The same for a fuel cell, the same for a Rankine cycle. That can be applied. And then you can increase the size. So you can apply for an industrial process, you can apply it for several industrial processes, you can apply it for a city, for buildings, for airplanes, for boats, exactly in the same way. Okay? So this is something which is quite generic as an approach. Okay, so now that we have made this analysis and we have something which is really powerful, except for something. The difficulty of plotting a curve and make it translate horizontally to another one. Okay? When I was a student, what we were doing was to plot the curve here, and then the other one on another sheet of paper, and then you cut the paper, and then you can make a very easy translation. Okay? But okay, it's not really practical. Okay, so we have to find another way to make exactly the same calculation, and that's what I'm going to show you now. And afterwards, I will do a break. Okay, so let's consider that we have the composite curve, which is calculated here. So what we can do is to consider that if instead of having the real temperature, we would correct the temperature by half of the delta T minimum. So I would do a translation in the vertical directions by changing the temperature of all the core streams by half of the delta T minimum. Okay? And at the same time, I would correct the temperature of all the hot streams by half of the delta T minimum, reducing the temperature by half of the delta T minimum. In this case, the big interest is that the curve will intersect. And calculating the intersection of two curves is something which is really easy from the geometrical point of view and the mathematical point of view. Okay? So it means that I'm going to change the domain. So instead of working with the real temperatures, I'm going to work with the corrected temperatures. The corrected temperatures are the hot stream, the hot temperatures minus the delta T minimum divided by 2, so half of the delta T minimum. And the corrected temperature of the cold streams are the corrected temperature of the cold stream plus the half of the delta T minimum. Okay? And in this case, the two curves will intersect. And how do I calculate this intersection, which is the place where the pinch point is? So, how I do it is the following. So, let's assume that I'm working in the corrected temperature domain. So, in the corrected temperature domain, if the temperature of the hot stream is higher than the corrected temperature of the cold stream, the heat exchange is feasible. Okay, in the corrected temperature domain, I do not have to add the delta T minimum, it's already done. Okay, so let's consider that now the MCP of the cold stream in a given in a given temperature difference, temperature interval, sorry, the MCP is bigger than the temperature of the MCP of the hot streams. So what does it mean? It means that the temperature, the heat load, if I'm working with fixed temperatures, the heat load of the cold stream is bigger than the heat load of the cold stream, of the hot stream, sorry. Okay? So it means that there will be a deficit that needs to come from higher temperatures. Okay? If I want to be sure that I'm feeding the cold streams in this temperature interval by whatever heat load, the heat needs to be at a temperature which is higher than this temperature here. So it means that in this case, what we say is that the heat of the hot streams plus the heat that will come from highest temperature will match the heat of the cold streams. And this temperature interval is in deficit. There will be the other situation where the heat in the hot streams will be higher than the heat needed by the cold streams. And in this case, in the same temperature interval, I will have a heat surplus. It means that there will be too much heat available in the hot streams. But this heat available can only be used by the streams that are at a lower temperature, so here below. So it means that now, if I'm looking in the reality, what is happening is that if I'm taking one temperature interval in the corrected temperature domain, I can write the energy balance over the interval here, which accounts for the heat that is coming from the hot stream minus the heat that is needed by the cold stream. I know that it might happen that I will have a certain amount that will come from a highest temperature, and depending on the balance, I will have a certain amount that will go down to the lowest temperature. So this is the principle of the heat cascade. So the heat can come from higher temperatures to lower temperatures, will enter into a temperature interval, will to some extent gain the contributions of all the hot streams here, will lose the needs of all the cold streams in the same interval, and the balance will be sent to the lower interval. And what I know from the thermodynamics is that the amount of heat that is cascaded here needs to go from the higher temperatures to the lower temperatures, which means that this flow has to be positive. We can never exchange heat from a lower temperature to a higher temperature. Okay, so it means that this flow has to be positive. And then what I can write is the expression of the calculation of the heat cascade, which is telling me that I would like to minimize the amount of heat that has to enter into the system, which is the minimum energy requirement of the system, that will be calculated by saying, okay, as soon as I have this amount, then I can calculate what is happening in the temperature interval below by taking this amount, adding the contributions of the hot streams in the temperature interval, and deducing the contribution of the cold streams in the same temperature interval. And I can do it for each of the temperature intervals, starting from the highest to the lowest one. Okay? And I know that this heat cascade has to be such that the flow is greater than zero. And the fact that I'm saying, okay, I would like to add the minimum, so which is the minimum amount that I'm putting in the system, okay, I know that there is a chance that one of these constraints will activate. It's possible that the first one is the one, so it's possible that I will be in a situation where I do not have to add any heat in the system. Okay? But by doing this, then I have a very nice way of calculating the heat cascade. There is an alternative formulation which allows also to calculate the minimum energy requirement by not doing the balance over one interval, but always with respect to the highest temperature. So I can do it from the highest temperature to this one, and then the highest temperature to this one, etc., progressively. And I will also be able to calculate what is the minimum amount that I have to add the system by identifying where is the minimum. Okay? That's an alternative formulation. So in conclusion, I have now, by introducing the corrected temperatures, the possibility of identifying exactly where the pinch point is, and I have the possibility of making it with an algorithm. Okay, and I'm going after the break to show you how to systematically develop this algorithm. The only thing that I would like to add to this is that by making this calculation in the corrected temperature domain, I have calculated the heat cascade that can be then plotted as a function of the temperature, the corrected temperature. So I can have a plot that says if I am in surplus of heat, and then here a deficit of heat with a cascade, and where I will be able to identify where the pinch point is located. So the pinch point is the place where the heat cascade is equal to 0, which justifies which allows me to define what is the minimum heat that I have to add in the system that I will read here on the top, which is the difference between this point and the y-axis. Okay, with the heat cascade plot is named the ground composite in comparison to the one that are here, which are the hot and the cold composite. And I have plotted two different plots here, the one with the corrected temperature and the one with the real temperatures, okay, which can be applied in or it can be calculated in plotted on the same plot. Okay, from there I have calculated the ground composites and I have been able to identify where the pinch point is located. So now let's make a break. If you have questions, I'm ready to answer. And just after the break, we are going to apply, or I'm going to show you an algorithm that allows you to make those calculations in a systematic way. Questions? Okay. So what we have seen is that there was a method that was able to identify where the pinch point is located. Okay, and so what I would like to show you now is how this method is implemented in practice. So what to do to apply the method. And just after my lesson, you will have to do the job by yourself. Okay, and I can tell you that I will not ask you to do it several times because, of course, all those things can be written in the computer. So writing this is easy in the computer, but I want you to do it at least once by hand so that you understand how it works. So how does it work? So this is the method that is named the problem table method. The problem table method is a very systematic way of calculating a heat cascade. So the way you do it is by first defining what are the hot and the cold streams, defining their heat load and temperatures, inlet and target temperatures. From there, you are going to first to generate an enthalpy temperature profile for each of the streams in order to define linear segments. And the reason why we do linear segments is mainly because to limit the number of temperatures to be considered. Okay. Once we have the profiles of each of the segments in the system, we compute the ordered list of corrected temperatures by reducing the temperature of the hot streams by half of the delta T of the temperature, delta T minimum, and increasing the temperature of the cold streams by half of the delta T minimum. Okay. Once we have this, then we have the ordered list, so which means that we can calculate the temperature difference in each of the temperature intervals. So I calculate the temperature difference in each of the temperature intervals. So it means between two successive temperatures in the list that I have generated. Now, from knowing the temperature difference, I'm going to make the list of the contributions of all the hot streams minus the list of the contribution of all the cold streams in each of the temperature interval that I will multiply, so it's the MCP, that I will multiply by the temperature difference of the temperature interval. And then what I'm going to do is that I'm going to make the innocent. I will say, what I would like to do is not to add heat in the system. Okay, so this is easy to do, so I'm going to say, let's assume that the heat that is entering the system is equal to 0, and I'm going to calculate now systematically for each of the temperature interval the heat cascade. So from the highest temperature to the lowest temperature, I'm applying this formula, which is in fact making deducing from the heat coming from above the contributions that I have calculated here in reality. Okay? And then I'm going to look at where is the minimum of this value. So if the minimum of this value is bigger than 0, then I'm happy because it means that I do not have to add energy in the system and everyone is happy with in the heat cascade. Right? If now one of those values here is negative, I'm going to look at the one that is the minimum one. Okay? So the one that goes into the lowest negative value. And I know that this value has to be positive, so what I'm going to do, I'm going to add a constant value to all the values that I have calculated. And this constant value will be such that the minimum will be equal to 0. So it means that I'm setting the heat that is entering the system equal to the minus the minimum value, which becomes a positive value, and I'm recomputing the heat cascade. And this value is the minimum energy requirement of the system, and the place where the minimum is located, which will be 0 in this case, will be the pinch point. Okay? So let's now look at how it applies to the example. So the first thing that I'm doing is making the inventory that I have already made once, okay? The inlet conditions, the outlet conditions, the MCP, and the heat load that is needed for the hot and the cold streams of the process. Now I'm going to calculate the corrected temperature, so it means that this is a cold stream that needs to be heated. So cold streams means corrections by plus delta T minimum, half of the delta T minimum, so 20 becomes 25, 130 becomes 135. Okay, and I'm doing it for the other cold stream, and then for the hot stream, it's minus half of the delta T minimum, half of the delta T minimum. It means that 160 becomes 155. Okay, and I'm doing it in a systematic way. So once I have done this, now I have the complete list of the corrected temperatures that I have ranked here. Okay, which means that I can calculate the temperature difference between the two temperatures. So 155 and 145 is 10, etc. Then I'm going to look at who is contributing. So I'm making now the list of all the streams, A, B, C, D, and who is contributing. So for example, here I have a hot stream that contributes by 2.5, which is the MCP contribution. And I can make then the sum of the contributions of the hot stream, and here, for example, minus the contributions of a cold stream. So it means that I have the sum of the MCPs plus 2.5, plus 0.5, minus 1, plus 3.0, plus 0.5, minus 1.5. Okay, which is just the results of the presence of the different streams multiplied by the, it's a sum of the contributions of the MCP. Now I'm going to multiply this by the temperature difference, which is here, to obtain the heat contribution. So I have here the MCP, so kilowatt per degree, that I'm multiplying by the temperature difference, and I'm obtaining the heat contribution to each of those one. Okay? From there, I will be able to be the innocent and say, so ideally I would like to put 0 in the system. So I'm putting 0 here. I'm receiving 25, so I have plus 25 here. I'm receiving 5, so I have plus 30 here. I'm deducing 50, so I have minus 20 here. I'm receiving 90, so I have plus 70 here. I'm receiving 5, so I have plus 75 here. And at the end, I have plus 45. Okay. By the way, the 45 is the 405 here minus the 450 that I had identified for the hot strings. Okay. So it means that I'm looking now for the places where this value is the smallest, and this is this here, and it is negative. So it means that I know that the system, this heat cascade is impossible. So I'm going to take this value and I'm going to add it minus this value here, and then I'm just adding. So I have 20 here, so I receive plus 25, so I have 45, etc. And now I have at the level of the pinch point 0 here. Which means that I'm better than you, huh? Because there was someone who has found 50 and another one 65. But in reality, I know that there is a solution that is going to spend only 20 to make the whole system, to do the heat recovery in the system. So I can go from the 405 kilowatt that were spent in the boiler to 20 if I'm doing the heat recovery. And this will translate into this type of composite curve. So this is the hot composite of the problem. This is the cold composite of the problem. This is the 20 that I need to add because of the delta T minimum here. This is the heat that can be recovered above the temperature of the pinch point, so above the 80 here. And this is the heat that can be recovered here below the 10 degrees, the delta T minimum here at 80 degrees C. And by balance, I have the 45 that was identified here. So 65 minus 20 makes the 45 excess that I have observed in the definition of the hot streams and the cold streams. And in addition to this, I'm able to calculate the heat cascade of the problem with the 20 that are entering, with the contributions of 25 plus 5 minus 50, etc. Okay, which allows me to have a complete way of calculating the heat cascade. So it means that now you are able to answer the questions that I have asked in the beginning of the day. What is the amount of heat that can be recovered? So the amount of heat that can be recovered is 295 plus 90. What is the amount that needs to be still added to the system is 20. And what is the amount that needs to be taken out of the system, removed by the cooling water, is 65. Okay? And it's systematic. So if you have 100 hot streams and 100 cold streams, you can apply exactly the same method. Right? Do you have questions? Yeah.
How do you know how you do it? How do you go from that to being like, okay, you need to install a heat exchanger here and a heat exchanger here?
You will have to come to the next lecture next week. So of course that's the remaining question. So what I know is how much I can recover and how much I will have to put in the system. But it's already a very good indication because I know now what can be recovered. Of course, the next question is what are the heat exchangers that needs to be bought and installed. So it means that this is still not answered. But there is something which is very important here, and I'm really happy that you have asked question, is that I can already learn a lot of things out of this first analysis. I must admit that I'm using a lot those composite curves before even starting to think about deciding which one of the heat exchangers will be installed or not. Because now what I know is what is the minimum energy requirement, but I know even more things. And the more things are the following. The first one is what we name the more in, more out. The fact is that the system is receiving today 405 kilowatt of heat and releasing 450 kilowatt of cold utility. Okay? And what I can tell you is that the amount of heat, the 20 that I have calculated, is going to tell me that the 385 kilowatts that I'm using today in excess to the 20 are in fact a certain amount of heat that is flowing in the system and it's released here. Okay? So what does it mean? It means that if I'm your boss, you can tell me then, you know, we are buying 385 kilowatt of heat for heating birds because it is not needed by the process, so I could only use 20. Economically speaking, okay? So this is this amount here, so the excess here is in fact an excess that is flowing through the process and that is released in the environment. Okay, this is the principle of the more in, more out. So the energy saving is in fact an amount of heat that is in reality used today to heat the environment. Okay, and then you translate it, of course, not in kilowatt, but in Swiss franc per year. Okay, and then you ask your boss, should I ask the birds or the fishes for the heat that I'm supplying to them because I have bought the heat. Okay, so this is a first important dimension because it means that you know now what is the target. That's what we name is the target. You know how far you can go, and the beauty of the approach was the delta T minimum. If you have calculated the delta T minimum, you know that this heat recovery, so the 385 that I have calculated here, can be done with a fixed amount, with a given amount of money that will be economically acceptable, predefined by the guy who has given you an interest rate, right? So it means that there is no reason why someone will say, well, it will cost too much. Okay, it will not cost too much because the delta T minimum is well chosen. It will never cost too much. Okay, it's a wrong assertion. Okay, you have made the assumption that the delta T minimum was well calculated, and from there you can ensure that the investment will make sense. Okay, a second dimension of this is that you have learned about the pinch position, and the pinch is a very special point. Why? Look at this. When I'm calculating the heat cascade, the pinch is at the position where the heat cascaded is equal to 0. What does it mean? It means that the heat of all the hot streams that are above the pinch needs to be used in order to heat the streams that are above the pinch. Okay? So it means that now I can use the temperature of the pinch as being a very nice indicator to debug a process. So when you look at the process, you know that every stream which is above the pinch, hot stream that is above the pinch, needs to deliver the heat to the cold streams. Okay? Needs to be used in a heat recovery heat exchanger. So now you have the list of streams that needs to be connected to heat exchangers, heat recovery heat exchangers. And in addition, you see that only streams that are above the pinch will use the hot utility. So it means that above the pinch, the process is like a heat sink. Okay, there is a need of heat above this temperature, which also means that below there is no need of heat. Okay, so if someone is heated below the pinch, it's not a good idea because I have enough heat. Okay, so this is what is happening below the pinch, and below the pinch I have to be just a little bit careful because below the pinch means also above the ambient temperature, because the ambient temperature is the temperature at which you can get the cold utility. Below the ambient temperature, then you know that you need a refrigeration system. Okay, but if you have to evacuate heat below above the ambient temperature, you know that you can do it with the environment. Okay, so it means that what we can see is that below the pinch, so starting from 0 here in the heat cascade, below the pinch, I have more heat available in all the hot streams than the heat that is needed by all the cold streams. Okay, so it means that below the pinch, the process is a heat source. It is going to deliver heat to the environment. Okay, or to any users that needs heat. Okay, if you have, for example, a city, you can heat the city with the heat that is available here. Okay, so below the pinch and above the ambience, the process is a heat source, and below the ambient conditions, then you have the refrigeration needs. Okay, so now you know exactly what is needed by the refrigeration cycle that you have already seen. Okay, it's only the part which is below the ambient conditions. So below it's a heat source, but needs refrigeration. So if I'm making this reasoning, then I'm learning something which is also very important, because it means that above the pinch, all the hot streams needs to be used above the pinch to heat up cold streams. Below the pinch, all the hot streams have to be used in order to preheat the cold streams. Okay, so what is the consequence of it? Is that above the pinch, if someone is cooling down a hot stream with a cold utility, so it means you identify a heat exchanger that is using cold water to cool down a stream that is above the pinch. So I have just realized that above the pinch, the heat of the hot stream needs to be used in a heat recovery heat exchanger. If this is not the case, it means that I'm cooling down, I'm stalling heat from a heat recovery, and I'm using it to heat up the birds. Okay, so it means that one of the hot stream, if one of the hot stream above the pinch is cooled down by a cold utility, then I will not have enough heat for the heat recovery here, and I will have to add this heat in form of an additional amount of heat. So it means that if I'm identifying a cold utility that is used to cool down a hot stream that is above the pinch, it's what we name a penalizing heat exchanger. It's a heat exchanger that is used to heat the birds. Okay? And you have here the balance. Huh? So the balance is saying that no heat can be cascaded here. So it means that the heat that is available here should normally be used for those cold streams. And if this is not the case, then I will have an additional amount of cooling that is needed somewhere. But especially I will need a certain amount of heat to be added in the system in order to close the energy balance of the needs of the cold streams. Okay? The same will appear if someone is heating a cold stream with a hot utility below the pinch. So typically cold water that is entering into the boiler directly without doing heat recovery. Okay? If a stream is heated from below the pinch from using a hot utility, what you will see is that normally you have enough heat available here for this one. So if you do not cool down this stream with the hot utility that you are using, well, you will have the penalty of having to cool more the hot streams. And again, it means that this hot utility usage here is in fact a heat exchanger that is heating the birds. Okay? That are all happy except if the temperature is increasing too much, right? But they are not paying for it, okay? And there is a third situation, which is a little bit more sophisticated or tricky, is a situation where you have a heat recovery heat exchanger between a hot stream and a cold stream, but the hot stream is above the pinch and the cold stream is below the pinch, okay? So what is happening here is that normally I should have used this heat for heating those streams here. But I'm using it here. So in this case, I need something to compensate. So it means that the amount that is crossing the pinch here is in fact a penalty. And in reality, you can see that this penalty that is used by this heat exchanger is also telling me that normally I should have used the red one here to heat up this one. but I'm not doing it. So it means that I have to cool more the hot streams, and therefore I will have to increase my cold utility. Okay, so it means that this heat exchanger, which is a heat exchanger that is crossing the pinch, is a heat exchanger that is a penalizing heat exchanger that is also some sort of a system that is heating the environment. Okay, so three types of penalizing heat exchangers in the system. Before starting designing the heat exchanger network, I can already debug my process, see where I'm losing the energy, right? And the answers is when I'm cooling a hot stream which is above the pinch with a cold utility, when I'm heating a cold stream with a cold stream that is below the pinch, and when I'm exchanging across the pinch, so when the hot stream is above and the cold stream is below. Okay, and never the reverse direction, because otherwise I would not be compatible with the delta T minimum. Okay, so those are what we name the penalizing heat exchangers. And to end up the analysis, I have to tell you that there are also hidden penalizing heat exchangers. And the hidden penalizing heat exchangers are the ones that are hidden in mixers. Okay, in a mixer, I'm taking a stream that is a certain temperature, so for example T2, I'm mixing it with another stream that is at T1, so for example hot water, cold water, making medium temperature water here. This is something which is done a lot of time. Okay, in reality, what is happening here is that the stream that is entering at T2 will be cooled down to T3, while the stream that is at T1 will be heated up to T3. So it means that I can replace, so this a priori was not showing a heat exchange, but in reality this is what is happening here. There is a hot stream, goes from T2 to T3, and a cold stream that goes from T1 to T3. And if the pinch point is in between, so if the temperature is, for example, here for the pinch point, it means that this amount of heat that is identified here, from T3 to Tp, is in fact above the pinch. Okay? And if it is above the pinch, it is a penalizing heat exchange. Okay? So it means that the mixer here is not well placed. And it means that I will have to take it so it is transferring heat across the pinch, and I will have to redesign the system in such a way that I will first recover the heat from T2 to Tp, and afterwards I will be allowed to do the mixing. Okay? But it means also that I will have to preheat the cold part here up to a given temperature here to compensate the heat that I have recovered here above the pinch. Okay, so it means that the mixers are penalizing heat exchangers that needs to be identified as well. And to some extent, it means that I have to be smart when I'm defining the hot and the cold streams, because I do not have to accept non-isothermal mixing. Because a priori, I do not know where the heat exchange will take place, where the pinch point will be. And therefore, as soon as I see a mixer like this, it is recommended to transform it into two heat exchange as a heat exchanger with a cold stream and a hot stream. Okay? So by this, I'm going to conclude and let you do the exercise. So what we have seen today is a way to calculate what is the maximum amount of heat that can be recovered when I have a collection of hot streams and a collection of cold streams in a system, provided that you give me the value of the delta T minimum that you have calculated just 2 weeks before. Okay? We have been able to show that as soon as you have an existing process, you are able to identify what are the penalizing heat exchangers. As soon as you know the position of the pinch point, there are 3 types of heat exchangers that are penalizing: the hot utility that are used below the pinch, the cold utility that are used, the cold utility that are used above the pinch, all the heat exchangers that cross the pinch, and you have to pay attention to the mixers. Okay? And we have seen a method that allows to calculate the minimum energy requirement of a system with limited effort by doing it in a systematic way. The method is named the problem table method and allows to identify the pinch point, the minimum energy requirement, and therefore the maximum heat recovery in a systematic way. Okay? So having said this, then you will have to do the exercise, which is similar to the one that I have made for showing you the problem table method, and have to identify in a given process the list of penalizing heat exchangers. Okay? Do you have questions? Yeah.
Just when we do the correction, we take delta T mean and we divide by 2. Why do we do that?
So the reason why I'm doing it is, for the moment, just because I want to share among all the heat exchangers a contribution to the delta T minimum. So it's to some extent, it's like to say that when you have a heat exchanger, okay, you have a contribution that is coming from the hot stream and a contribution that is coming from the cold stream. Okay, in 2 or 3 weeks, I will show you that this has another meaning because it corresponds to some extent to a delta T minimum that is associated to one stream. Okay, and I will make the link between this delta T minimum associated to one stream with the heat exchange, the heat transfer coefficient. That can be different if you have 2 liquids or if you have a gas and a liquid. The gas is more difficult than the liquid, which means that you will have bigger delta T minimum for the gas than for the liquid. And that's why I'm doing it like this. So for the moment, we just assume a equal distribution. Today, I could have said that I'm just correcting the hot temperatures. Okay? Good question. You have other questions? Yeah?
The moment, if we do an exchange, we had that in the single size, it's T hot has a temperature that is T out, has a temperature greater than T cold in. Is that the case of penalizing heat exchanger?
No. The penalizing heat exchangers are only defined by the location of the pinch temperature. So it means that if I'm going back to my example that I have solved with you, so I'm going back here. So a penalizing heat exchanger would be a heat exchanger that is using heat that is, for example, using a cold utility here above. Okay? Which is always the case in your case, because all your hot streams are cooled down by cooling water. So it means that you know that the 2 heat exchangers there have to be replaced. Okay? The same, the cold utility which is used, the hot utility that is used below the pinch. Okay? And again, you have only boilers for heating streams, so you know that there will be a part that needs to be taken out. Okay? And of course, you do not have process heat exchangers in the small example, so you do not see a situation where you would heat something with something which is there. Cool down the stream here to heat up something which is there. But it's possible that if in the solutions that are presented here, there is part of this kind of penalty. Could be 1 or the 2 or the 3. Okay? Other questions? Yeah.
So just by looking at this, can you tell anything about like number of heat exchangers that you will be
come to my lecture.
Because wouldn't that affect the cost calculations?
Yeah, I will explain. In fact, yes, my answer is yes. I can tell you, and I will explain you
I
next
mean,
week.
I'm just wondering if that would affect the DT-min calculations because changes cost.
Next week. Everything will. So it's good to have those questions because they, to some extent, is a good introduction of what I'm going to explain next week.
In this case, would it be possible to reduce the delta T and get rid of the boiler process? That way saving some other cost.
This one would be really difficult because it would mean that that I would have to. So I cannot give you the real answer, but it means that I would have to translate this curve further here until the time where I'm reaching 0 here. Okay, so it means that I would be somewhere like this. So apparently it's possible, but with with small temperature, very small temperature difference. But it's not impossible in this case. Okay, so it means that I would really go from, so the 20 are expressed here, so it means that it is ending up somewhere like this, here. So you would have, I don't know, 5 degrees C, and then it would balance. And it's not impossible now. But then it depends on the economic conditions. So I've taken the 10 because it's easy for me to explain. Otherwise, I would have to, here, I would have, especially here, to explain how I'm going from 20 to 22.2 to 6611. Okay?